Thanks very much for inviting me to talk a little bit about ASM for NMR. Yeah, Mestrelab has been committed to fair data for a long time, so this is maybe a sort of a stepping stone along the way to more fair data. So quite a few of you know me, some of you don't. So I was at GSK for a long time. My role was hybrid informatics, analytical chemistry, and then over time it became not very hybrid at all. It was nearly all informatics because we were being driven by the need to automate labs. And as part of that, I'm sure a lot of you will remember with great joy my membership of the Allotrope executive and also the GSK representative on the Allotrope board. And at that time, I was a very strong proponent of ASM, and I am really pleased to see that it's got so much traction as we've been going on in subsequent years. So I left GSK 3 years ago. I'm now a consultant working with Mestrelab SciY, and hence that's my interest in this presentation. So actually, I probably don't need to talk about the problem because Frederick from BASF actually outlined it very nicely. We have a large number of instruments, even instruments which are doing the same sort of job, and they all have their own software. They all have their their own data format. And as analysts, we probably live with it because that's our job. But the end users of the data really don't want to have to deal with that data from lots of different sources and have lots of different software on their PCs. And actually, that was how Mestrelab started. It was a group of people at the University of Santiago de Compostela, and they had exactly that problem. Their chemists had to actually go back to the instrument to process data. So they created this product, which older people will remember, a thing called Mestrelab. And they also made it more widely available. It was really popular. Everyone wanted to do something with it. Everyone wanted enhancements to it. And they realized that they couldn't do that as a hobby project. So they then founded Mestrelab at that point. And 3 years later, they released the newer version of the product called Mestranova or MNova. And that supported a whole range of different NMR formats. And in subsequent years after that, people said, well, what about LCMS? I really like LCMS and vibrational spectroscopy. So it was extended to do all of those things. One thing that I'll come back to here, which is very relevant to the BASF use case, is that they created some automation tools, a thing called M-Gears, because as we'll see, creating ASM files is often part of a data pipeline. So ASM for NMR was released in May this year at Mestranova 16, and it supports both reading and writing of ASM files for NMR. And some people say, well, why bother with NMR? Let's face it, there's only 2 vendors these days. There's Bruker or Jail. Well, first of all, that's not entirely true. There's a whole load of benchtop vendors these days who are adding complexity to our universe. And people still have variant/Agilent instruments producing data. So there's data coming from those. And if you ever want to go back and do your backlog, then you've probably got most of these things here. So MNova will be able to read these things. And of course, now it can just write them out as an ASM file, which is great. So while we're not talking about LCMS today, maybe sometime we ought to, because I would like to see us do the same thing for LCMS. Because that's an even more muddied and complex environment. So maybe that's something we should work on at some point. In terms of standards, well, we already had a standard. I mean, JCamp DX had been around for a long time. It's sort of the granddaddy of NMR data standards, or even it started off with infrared actually. So why not use that? And I think it was Ben Wolford-Lim. So I'm going to call you out on this one, Ben. He looked at the paper on it and he said, well, it's more like a set of recommendations than a standard. And it's true, it was implemented in lots of different ways. So it was not a great standard. And even though it survived the test of time, it was written in the days when people used Fortran as their coding language. And so it's relatively easy to parse in Fortran. It's actually quite hard in most modern programming languages. There are other ones. So the ones in red are the ones which are supported by Mestrelab there are other ones out there. NMR data is an interesting case, and we'll come back to that because it's one of the things I'd like us to investigate going forward. That's more about storing assignments, so assigning structural features to spectral features. But anyway, ASM is great. So, and I probably don't even need to speak to this one because the Frederick from BASF has just given a really good reason why you want to have a standard. You've got all these variety of different things coming in, and you want to have a standardized data processing pipeline so you can aggregate the data, and in the process of aggregating the data, know that you're going to be comparing apples with apples, not apples with oranges. So these are quite key. And another thing that would be very nice to have is that I know from my perspective, we used to keep everything as PDFs because that was long-term readable. And a PDF, I don't know if you ever tried to look at an NMR PDF, but it's the most frustrating thing in the world, and you can't do anything with it. Whereas with ASM, we could actually store a data set which will be long-term readable and will enable us to be able to interact with the data properly in the future. Do I need to explain ASM? There may be someone on the call who's not come across it. I know it's been mentioned quite a few times. It stands for the allotrope simple model. It's a JSON representation of the data, and I'll again briefly touch on JSON and why it's good and also why it's bad. But the key thing here is it's based on the rigorous allotrope ontologies, and this is, I can't emphasize this enough, this is really key to making sure that we are comparing apples with apples as we go through the system. Not just within, say, the NMR world, but across the wider analytical world where we have definitions for things that we stick to. So that's really key. And for those of you who wanted to see some JSON or an ASM file, here it is in all of its glory. And this is the header or the first few lines from an NMR ASM. And as you can see, it's human readable. More importantly, it's machine readable. But it's also quite chatty as well. So that's maybe one of the things that we'll talk about in a little bit. JSON, I'm not going to get into the wars JSON versus XML because everyone has an opinion. But JSON is designed around data objects, whereas XML wasn't designed to do that. It was a document markup language originally. Yeah, I think JSON is probably better suited to what we really want to do. It's very easy to parse. Every programming language, almost every programming language could parse JSON very, very simply, either using its built-in functions or using third-party libraries, which are readily available and free. It's easy to validate, and this used to be one of the big things for XML, so that you could have an XML schema, which would make sure your XML was well-formed. Well, you can do that for JSON. So there are JSON schema, and you can actually check that your JSON file that you've created is a well-formed JSON file, which is great. And everyone uses it. You just need to search your PC and you'll find hundreds and thousands of JSON files on your PC. What's not so great about it, it is quite verbose, maybe very verbose. It's not quite as bad as XML, but it's pretty close. And there are a few other slight technical things, but nothing which affects our ability to use it for NMR. But I'm sure if we get the techies in a room, they would probably argue about pros and cons of how you represent doubles or whatever. But anyway, that's the main downside is it's big. Okay, so again, going on to the automation, I could read a file into Mestrelab and I could save it as an ASM file. I'm not sure that would actually gain you that much, but it really comes into its own when you're doing it with automation. So you could do Python scripting within MNOVA, for example, to create your own automation workflow. Alternatively, if you don't want to get your hands dirty, then MGears is a no-code automation pipeline. And hopefully I'll show in a second different ways that we can do that. So I've got two use cases that I'll just very quickly demonstrate. One would be doing your backlog conversion. So you decide, actually, I want to have all of my backlog information as ASM, so I can then do some data processing on it. That's one case. And another one, once you've done all that with your backlog, you may want to do it dynamically on the fly. So as soon as a data set comes in, you just convert it and create an ASM for it straight away. Okay. So this is the first use case. This is the backlog conversion of a set of files. So I'm just going to use the M-Gears automation to do this, and it's got two different modes. It's got effectively backlog mode, so it will go through and just do everything, and then there's a real-time mode. But basically all you do is you just point it to the folder. So this is the folder where I've got the data. You can put some filters about what sort of things you want to process, and then there's a plugin. It's a brick which says convert to ASM, and I can just set that running. And what MNOVA does, or Gears does, is it checks the validity of the folders, that they exist and they've got stuff in them, and then it will go through, analyze what's there, work out how long it will take to do it, and then start doing the conversion to ASM. So you'll see the ASM files just start appearing in here. You can see it's about, so this is going to take about 20 seconds to do these 5 data sets. And that's great. You know, if you've got a backlog, you set it going, and you come back, and this will just shut itself down when it's done the last one, and you know that it's all finished at that point. So that's quite handy for doing the backlog. And if you don't want to do your backlog, I've also got another folder here. So I'm going to pretend to be a spectrometer for a second. What I'm going to do is I'm going to drag and drop some files. So it's just simulate what a spectrometer would do, because I don't have a spectrometer at home. So this time I'm going to do real time. It's the same thing here. Here you can put a whole load of different places for it to look. Everything else is the same. It's still got the same plugin. And I can run this, but the difference this time is obviously there's nothing in there at the moment, so it's not going to start trying to convert, but it will wait until a data set comes in. And when a data set comes in, like this, oops, did I drag that? No, I didn't drag that. There we go. I can't operate Windows. Okay, so I can drop this in here, and it will see it straight away. It checks to make sure that it's been written, because obviously if you want to monitor real time, you don't want to start trying to convert things before the experiment is complete. So there's a whole set of tools for doing that. And you can see it's converted that one. I've now run another one. It's converted that one. I'm now bored as an instrument. I don't like that job, so I just dump the rest of them in there. So these will go through and convert, and it will just stay there running in the background, and it knows which ones it's converted, so we'll try and convert the same ones again. So anything new going in there will get converted. Okay, so this time it won't shut down either, because it's still waiting for new stuff. Okay, so I'm going to shut it down manually. I suppose I ought to show that we can actually open it. So I'm just going to drag and drop an ASM file into MNOVA. And sure enough, there it is. It's a nice NMR spectrum, which we can do something with. And it also can handle multiplets. So if I do a multiplet analysis on this and then save the ASM manually, so I can do that. Save as ASM. Incidentally, the extension doesn't care. Mestrelab knows, it analyzes what the file is. So here's the new file it's just created. If I drag and drop that one on there, hopefully we should see an NMR spectrum with the multiplets as well. There we go. Okay, so a few things to just point out. ASM is not a page definition format. I often get asked this, oh, can I save page layouts? It's all about the data. Quite honestly, I believe that's exactly what it should be. We don't have chemical structures stored within ASM files currently. I don't suppose there's any reason why we couldn't, but actually the real benefit would come if we could assign the NMR features like multiplets to structural features like to a proton, for example, similarly to the way that NMRE data happens. And I would really love to see that capability in there, because it would then make the format much more widely usable. One of the things we've noticed and also got fingers burnt on ASM rightly demands units for parameters, as it should do. However, in Bruker and Varian NMR data, the temperature has no units, which is bad. What's worse is Bruker defines its temperatures to be Kelvin, and Varian as degrees Celsius. And so we came up with some very interesting conversions as a result of that. So we have to infer this from the vendor of the data, which is not a great thing to do. I mean, obviously we can't do anything about it. The vendors, it would be nice if they actually were slightly more thorough about how they store their data. And as I mentioned before, ASM files can be big, so they're not suited to very large data sets, but they do zip up nicely. But we probably want to look at alternative approaches. And I think we've just had this conversation sort of in that NMR is more complex than most because you've got the raw data, the FID that you create, but when you Fourier transform it, you create real and imaginary cubes. And these are things that we really want to find a way of having a uniform way of how we approach that. And I say that's a discussion. It actually gets even worse for 2D NMR, where the raw data is actually relatively small, but when you Fourier transform it, particularly if it's phase sensitive data, you end up with 4 quadrants. So you end up with at least four times the amount of processed data. So these files are very big. And often for NMR, you can do non-uniform sampling, which means that your raw data is pretty tiny, and then by the time you've processed it, it is absolutely massive. Okay. So yes, talking about this, so I thought I'd do a few experiments. So just to give an indication of the size of the data set, currently the ASM which is being generated by MNOVA is 27 megabytes in size, which is big for a 1D, especially as the original data is only 1 megabyte. So that's not great. It does zip down, as I say, down to 3.1 megabytes, which is better. And incidentally, you can drag and drop or open zip files directly in MNOVA, and it works out what to do with them. But either way, that's not great. So I did an experiment. I extracted out the 1R, the 1I, and the FID files from it. And if you extract them and have them as separate CSV files with a lightweight ASM, so you just have a pointer to those files, it comes down to 4.5 meg. And if you used a binary format like HDF5, then it comes down even smaller, but maybe not enough to justify you dealing with binary data. That would be the only thing I would say. So it would be really nice to have a way of handling these large data sets, particularly 2D data sets where it's much worse. Okay. Okay, summary, yeah, we can do it. It's easy to parse. We can do backlog conversion. We can do real-time conversion. And we do remain committed to supporting the Fair Data Initiative and getting involved in these conversations. I noticed lots of things are sort of coming in on the chat, and maybe we'll deal with those. But I think the conversation is a much deeper conversation than we'll manage today, but it's worth having, I think, as we go forward. I would like to thank Merck, who have been absolute prime movers in this, and they've actually made this happen with Mestrelab. So thank you to Merck for making it so. And I also like to thank the Mestrelab development team, particularly Marusha, who did most of the coding for it. And I'd like to thank you.
Thanks again, John. Great presentation.
Thanks.